Hi, we're going to do the concepts video for determining an equilibrium constant. So the whole point here is to determine a Kc for this particular reaction. This is a complex ion, and it's simply ferric thiocyanate or iron 3 thiocyanate. This is the thiocyanate polyatomic ion. Of course, this is iron 3. Now, a few weeks ago, you did a study of the alcohol content in beer and in mouthwash using Beer's law, okay? And remember what you did first was develop a standard curve where you made a set concentration, which went on the x-axis, and you measured the absorbance of the solution on the y-axis. Okay, so this concentration you set, you determined, you made the solutions, and then you measured the absorbance for each of them. And when you did that, you came out with an equation of a line that was very similar to this. Remember, y equals mx plus b. And b is obviously a little bit of an error factor, because if you end up with no b, you have done an amazing job. So just like last time, absorbance was y, and the concentration was x. And your slope was eta, the molar absorptivity, times L, the path length. Now the path length is 1 centimeter, so we can effectively say that the slope is equal to eta, or the molar absorptivity. And in fact, last time, we didn't worry too much about this particular slope, knowing it exactly. This time, we're going to be determining that. That's the very first part of the lab, is determining eta, or determining the slope for this particular graph. So again, just like last time, you're going to be doing a standard curve with known concentrations of iron and thiocyanate and iron thiocyanate. So this is a colored species. Complex ions are always colored species, and this one is orange to red, depending on how concentrated you make it. Okay? All right, so what we're going to do, these references are great, but they're to a previous edition's Coates and Treichel. You can still find them on our Coates and Treichel. Okay, so let's take a look at what we're going to be doing. Again, we're going to be doing the standard curve first. And in order to do this, we're going to have to make up exacting concentrations. Exact concentrations. Now, this is going to be kind of interesting because we're going to be using something called, I think you've seen this before, Le Chatelier's principle. Okay, Le Chatelier's principle. So again, we're still, what we're measuring the absorbance of is that iron thiocyanate complex ion. So we're again using this equation, which is in equilibrium with that iron thiocyanate. Complex ion. Okay, so here we have our equation. What we need to do is know the concentration of the iron thiocyanate and then measure its absorbance. And once we do that, we can have our standard curve. Okay? That's what we need to do. But the problem is, we don't have iron thiocyanate sitting on the shelf. We have iron 3 plus that we'll know the exact concentration of, and thiocyanate that we'll know the exact concentration of. So how to figure out iron thiocyanate? Well, let's take a look down here for a minute. Getting myself a little bit of room. First of all, these are our directions for actually making the first standard curve solutions. I've just moved them down so I can use some space. First of all, notice here that it says dilute iron 3 nitrate. Now remember, iron 3 nitrate is a strong electrolyte, so we're going to end up in solution with iron 3 plus and 3 nitrates swimming around doing nothing, okay? And this is what we care about. So we're going to be using dilute iron 3 plus. Well, that's going to be interesting because the bottles out on your benches are not going to include dilute iron 3 nitrate. That won't be there. And the reason that won't be there is because you're going to have to make it. And the way you're going to make it is right here. You're going to be pipetting this solution, which is on your benches. You're going to take 4 milliliters of this, and you're going to put it into a 100 milliliter volumetric flask, and then add nitric acid until the bottom of the meniscus is at the 100 milliliter mark. And then you're going to mix it up. Okay, that's fine, easy enough. But in order to then find the concentration of the iron, we've got to find the concentration of the dilute iron. And this is the dilute. Whoops, dilute. We don't know what it is. So we're going to have to use our M1V1 equals M2V2. So to begin with, what we're looking for is the concentration of iron 3 plus dilute. This guy right here, first column. So M1V1 equals M2V2. Well, we know M1. M1 is right here. So 0.0025 molar times volume 1, 4 milliliters. So I'm going to leave it in milliliters because this is milliliters too. So 4 milliliters. And that is going to equal M2, which I don't know. This is what we're solving for, times V2, which is 100 milliliters. Okay, so our M2, and now I'm just going to use what it is, Fe3 plus dilute is equal to 0.0025 molar times 4.00 milliliters divided by 100 milliliters. And when you do this, I want you to go ahead and do this right now. But I think you're going to find that it ends up being 1.00 times 10 to the minus 4th molar. That's pretty small, right? Okay, so now we know our concentration of iron 3 plus. So now we can actually write it in. Okay, and I'm going to write it in right here. So 1.00 times 10 to the minus 4th. Okay, so now we have our reaction mixture going on. Oh, why did I use nitric acid? Well, when you think about it, here we've got iron nitrate, iron 3 nitrate. So I'm just using something that I've already got in there just to make, it's almost like diluting it with water, except for it's got that nitrate, so I don't mess up the electrolyte balance. Okay, so now let's take a look at tube number 1. we're trying to find the concentration of iron So in tube number 1, we're starting with our dilute iron, and we know its concentration, which is 1.00 times 10 to the minus 4th, and we know its volume, 1.00 milliliters. It's now divided by the total number of milliliters, which is 1 plus 5 plus 4, or 10 milliliters. So our initial concentration of iron for test tube 1 is 1.00 times 10 to the minus 5th. For tube 2, we're going to do the exact same thing, except for this time, we're going to be using 2 milliliters of your dilute iron, so you'd end up with 2.00 times 10 to the minus 5th, etc. And you can see it's 1 milliliter, 2, 3, 4, 5, so this is actually going to be a really easy concentration to find once you've found one of them. But now comes the problem of, in order to find our standard curve, which is absorbance versus concentration, it's not concentration of Fe3+, it's concentration of FeSCN 2+. That's what it's the concentration of. And like I said, I don't have that sitting around in a bottle in the shelf. I have to make it using this equilibrium that I have up here. Well, let's go back to this and see if we can figure out how Le Chatelier's is going to help. Well, I know this for sure. And if I take a look again at what I'm putting in here, putting in my SCN, but check it out. You know this is 1 times 10 to the minus 4th. This is 1 molar. So this KSCN is a huge excess, a huge excess. So if we have a huge excess of thiocyanate, we're going to be forcing practically all, effectively all, of the iron to become iron thiocyanate. That's why we're flooding it with this SCN, so that we can say whatever our concentrations are in these test tubes of dilute iron, that's the same as the concentrations of our FeSCN. Okay, so let's come down here to a table. So we're going to, now I've got my data table here, but here I have my test tubes filled, test tubes 1 through 6. These are my known concentrations. These are the concentrations that I just solved for with you above. Now, because of Le Chatelier's principle, because this is the limiting reactant, and I have flooded this test tube with extra reactant, effectively we can say that the iron thiocyanate concentration is going to be equal to the iron 3+. So that's what I've done here. Test tube 1, we figured out that was 1 times 10 to the minus 5th, so that's what the iron thiocyanate is, etc. for all of these columns, all of these different test tubes. Now, what you've done, of course, once you make these, and you have to follow the directions exactly, you're going to have to measure their absorbance. And it's the same thing you did back with beers, except for you're using 450 nanometers this time. So it'll be the same thing. But here I've just plugged in some make-believe numbers. Don't use them because they probably won't work. Plugged in some make-believe numbers. And this is what I'm going to use. This is my x-axis. Those are my x values. And these are going to be my y. And when I plug those all in, I'm going to end up with, eventually, an eta. Okay, we've plugged in all those absorbances that we measured. We've plugged in all the concentrations that we made, and we got a slope. And again, this is made up data. 12,500 was my slope. Okay? So far, this has been pretty straightforward. Now, I'm not going to go through all of this with you because we're going to finish that up in the calculations video. But I want you to know what you're doing next. After you make this standard curve and find your eta, you're going to come back up here and make your next set of test tubes. And this set of test tubes is using a decent sized molarity of iron, not your dilute, decent sized molarity. And look at that, not a huge amount of KSCN either. Okay, these are going to be the same molarity. Now the volumes we use are going to change. And this is just that extra to keep everything equal in the electrolyte. Okay, so same concentration of both thiocyanate and iron 3+. You're going to find your concentration of iron the same way we did before, which is M1V1 equals M2V2. In this case, you have molarity for iron 0.0025 times your volume 2.0 milliliters. Well, you're actually going to have the extra O, equals M2 divided by the volume total, which is 2, 4, 14. And it's going to be 14 milliliters for each of these. That cancels and is going to give us our new molarity. So this is going to end up being molarity 2, which is equal to your Fe3+. This is going to be 3.57 times 10 to the minus 4th. So let's go ahead and look at this next table. Well, I didn't put in those concentrations. I made up the samples exactly the same way that I made up the first set that was my standardization curve, and I measured the absorbance exactly the same way. Now this time I'm not going to be putting them on the standard curve or anything. I'm going to be using the absorbance equals whatever your eta is, and L is 1, so we'll put that in there, times concentration, and then whatever your little mistake is. So you're going to end up with absorbance, this guy, minus whatever your little mistake was, divided by eta is going to be your concentration. Cool? So you're going to be able to solve for your concentration of your FeSCN for all of these test tubes. Now, why can I solve for FeSCN using experiments for this part, whereas the first part I could just use Le Chatelier's principle? Because this time on this, I am truly taking equal amounts almost of my iron 3+ and my thiocyanate, and I am truly making an equilibrium with complex ion. I am not flooding with either one of these, not giving you too much iron, not giving you too much thiocyanate. So we can actually end up using an ice table for this. Yes, you're going to make a lot of ice tables. Let's take a really quick look at the first one before I let you go on this. So again, Fe3+ plus SCN minus is in equilibrium with your complex ion. Now, when you start out, you're going to know, see there's that 3.57 times 10 to the minus fourth. You're going to know, because you can calculate these concentrations. Okay, we're literally doing an ice table. Okay, so test tube number 6. Let's bring it on down. Oh, there is one right there. So let's see, test tube number 6. Our initial concentration here is 3.57 times 10 to the minus fourth. And if you look at your SCN, you'll also see that it is 3.57 times 10 to the minus fourth. But when you made these solutions, did you put in any of this iron thiocyanate? No, you didn't. So it is absolutely 0. And now, as always, minus x, plus x. And now you're going to be figuring out from that absorbance way up here, these absorbances of your unknowns, or of your FeSCN, and then the calculation for the FeSCN, you're going to know what this FeSCN at equilibrium is. In other words, you're going to know X. That you're going to know. And once you know X, you can find each of these iron 3 plus at equilibrium and thiocyanate at equilibrium, and you can get your K, right? Because K equals the concentration of FeSCN, just from our equation right here, over the concentration of Fe3 plus times the concentration of SCN minus. Okay, so that is what we're going to be doing. And I'll be there to help you. So if you get confused, if you're struggling a little bit with this, it's okay. I'll explain it to you again before we start the lab. Now, as far as the pre-lab goes, what you need to understand is that the pre-lab is pretty much completely ice tables. The first thing we're going to do is ask you to do the K equilibrium for this particular reaction. Oh, I just did that right there. The second thing we're going to do is ask you, hey, I've got a bunch of equilibrium data, concentrations, so when I plug it in, what's my K? There you have it, right? We know how to do that. Then their next 3 problems are just little variations on the theme. You're going to know your equilibrium constant expression, and you're going to know your K equilibrium, and so you're going to be able to do the next few problems where we change up the concentrations a little bit here or there. So go for it. No problem. You're going to have just had an exam or about to have an exam on equilibrium. So all we're doing here is showing you how we figure this out experimentally. So I'll see you in lab.